Yeah, so let me put the topics a bit into the context. So we are part of computer science, right? Or informatics, as my colleagues here in TM like to refer to call it. So computer science actually has a lot of different fields by now, right? It's really ubiquitous in our environment, thanks to things like mobile devices and so on. We have it everywhere, starting from theory, databases are classical topics, networking, or algorithms. But what in a way is closest to what we'll be dealing with is computer graphics. So showing, visualizing things in the computer, and that by itself also has drilling down a variety of subfields. The classical one being to display things on screen, the rendering aspect of it, which actually will play a minor role in the game physics setting. We typically will produce something that will be shown on screen, but we will not deal too much with the question of how to really show it realistically. That is more a question of rendering algorithms. And actually, if you think about it, in a way, rendering is also a physics simulation, basically how light bounces off inside of a scene, how it reflects and refracts on complex surfaces. But yeah, we will not deal with these simulations so much, but rather with motions over time. Geometry is another crucial aspect. How do we actually describe a certain shape, three-dimensional shape in the computer? Also non-trivial. Here you can see one example, one answer that's very popular, and that is the good old-fashioned triangle. This is one of the primitives. Right, this is nice for a surface, and if you want something in 3D, then we need a tetrahedron, and in 4D, it's a bit more complicated. But dealing with surfaces in 3D, triangles are, for example, a good representation. But this is also not a trivial question what to choose and how to best work with geometry under certain constraints or application settings. What we'll be dealing with is animation, so meaning we're interested in not only some static geometry, but in how do things actually change and move over time. And drilling further down, there's a variety of different ways to approach that, from manual specification of motions to mocap. But the goal of this course is to leverage physical models to move things over time. That would summarize as the main goal of the algorithms we'll be talking about, which you can actually see as a kind of specialized procedural way of animating things. Yeah, it's also good to think about animation is actually an old word. It comes from breathing life into it. I think it's a nice thought. And hence also traditionally characters, right? Here's a good example from Monsters University, are a target here. However, I'll come back to it in a moment. We'll be dealing typically with non-animate characters, so materials rather than characters who act on their own, rigid bodies or things you would find in your environment, at a wall basically, things like that. Yeah, what also plays an important role in this setting is for interactive applications. We typically have situations where a player or user inputs commands and has a large flexibility with respect to what he or she can do. Hence, we typically cannot just pre-compute or manually create all the different aspects of it, but we need to compute on the fly, and in a way, this is where the physical laws come in, where they're so great, because these physical laws, right, think about Newton, they are not tied to a specific application or one specific setting, but they're really fundamental laws of how our nature behaves. And as such, if we can compute these, then if we do it right, we also can very flexibly deal with all kinds of situations in a computer. So this is where the simulation aspect comes in. In a way, it's kind of leveraging these fundamental laws for general and flexible simulations. Well, we do need to compute it right there on the spot with a certain frame rate while the program is running. So there is an inherent trade-off, and as one of the topics we will be getting back to a lot, we need to make sure things are fast enough to actually run in essentially real time or even much faster. And that is a bit of a trade-off between how accurately we can compute the solutions while actually ensuring stability. Right? The nicest simulation does not give me anything if it's blowing up and not showing on screen. Yeah, also beyond traditional computer games, these physical simulations really do play a large role in a variety of literally all kinds of interactive settings, whether it's training applications. Think about medical simulators where people need to understand certain behavior of how tissue behaves. So people learning about physics, being able to interact or kind of virtually run virtual experiments, or the game setting to basically entertain people. This is another nice way to think about it a bit, similar to the point I had before. You can think about animation or the modeling of content in interactive settings in terms of this pyramid. At the very bottom, we have the geometric aspect, right? So purely describing the shape of the pyramid or so. Then we can compute kinematics in a way, pure forward motion over time. And we will be targeting this middle level here, the physical level, where we have physical laws that tell us about interactions, changes to the environment. The next layer of complexity here, but also the physics is not the end, right? If you think about, as mentioned before, going towards characters, we could, based on these physics, then start to model behaviors, having agents with certain own goals and behavioral aspects. And traditionally, what you could see as the last bit to close these models is to also model the cognition of these agents. So, right, like us basically seeing, being able to touch and feel certain parts of our environment, and letting the agents interact with the physics based on their behavior and their own cognition. But here we will actually focus on the central level. Yeah, let me explain a bit more these different ways to do animation. That's also worth a few comments to motivate a bit why these physical models are interesting and important in virtual environments. So one of the most traditional ways to move things, especially for example for movies, is a keyframe animation. So here's a nice example of a ball. It's essentially a bitmap, and we place certain keyframes over time. If we're smart, we don't place one for every single frame of a 100-frame sequence or so, but we place a few and then interpolate a smooth trajectory across these. But nonetheless, this is a very manual process. So in a way, that's great. We have full control. We can very exactly specify for every instance in time where this object, this ball, should be. But this is pretty tedious. I'm sure you can imagine if I have a single ball, it might be okay. You can let that bounce around. Even then, it's sometimes not even that easy to really get it right, but this is definitely not interactive. Right? Then I have one fixed trajectory. This is very difficult to make it flexible, but nonetheless a traditional way and a very controlled setting. As mentioned before, motion capture is another interesting aspect. I have to move a bit. So here the goal is that, or the kind of starting point is that we start with a real person or object, some real thing that we want to capture. Traditionally, we put markers on it. These technologies have improved quite a bit, but nonetheless, we somehow need to track points on the object. Those are reconstructed in 3D in the computer. As you can see in the second picture here, and giving some kind of rough skeleton. This we can transfer to some rigged model, for example, of a character, and this rig would then drive the actual mesh, kind of more or less smoothly interpolated hull for the rig. And yeah, the nice thing is now we can really get data from a real performance. What's a bit tricky is that this produces a lot of data typically, needs to be cleaned up and worked with. And what if we want something crazy, like a flying elephant or a dragon or so? That's difficult for a mocap setup. So in a way, it also restricts us to things we can actually capture in reality. And again, this is not interactive. I get a real performance, but if I want to make this interactive, I basically have to really go in and capture every possible behavior that I might anticipate in a game, which is actually what many of the sports games did. They have vast libraries of motions, but again, this leads to a certain authoring and capturing workload beforehand. Yeah, this is in a way where the physics nicely come into the picture. So physics-based animation now uses these very generic laws and lets us then vary the behavior based on these principles. So here, picture is a very classic one, rigid bodies. If we choose the right ones, the right physical models, then we can actually compute it in real time, but typically this requires quite some calculations, so this is potentially much more expensive than the others, where we basically play back some pre-recorded data. And the nice thing is now we can let forces or situations flexibly change here within that physical setting. We will just get a different solution, but this is in a way no problem for such a solver, right? If we can afford to compute them on the fly. Yeah, looking ahead a bit, what I think is now actually a very interesting outlook, especially to reduce the complexity of the real-world physics, is to have learned models that capture the most important bits. And right, for example, to use neural networks as function approximators, giving us solutions to these physical models. This is actually a very interesting research topic that I'll come back to once in a while over the course of the lecture. We will be focusing on the kind of traditional way of modeling from known physical laws and finding solutions. In a way, these machine learning applications are a step on top. In practice, it's typically not a good idea to use any machine learning if you don't know what you're dealing with. So even if you're interested in going towards kind of deep learning driven physics simulations, it's typically important to know about what would a normal model and a normal solver do to make the transition to a learned one, like in other fields for learning. But nonetheless, I think it's a very interesting outlook. Another note that's important here is that by physics here, of course, we don't mean basically don't mean everything you would normally deal with when studying physics at UM or so. Right? So what we are dealing with here is actually one very specific field of physics, namely traditional mechanics. That's what we'll be focusing on here. Nonetheless, this is also part of a physics track typically, but we won't go into other topics like astronomy or electronics. So there's all kinds of topics around this that could be interesting in a physics setting. So we'll be focusing on mechanics. Nonetheless, I think a very interesting aspect of physics. Yeah, now I have a bit of a summary slide to summarize the goals of this lecture. Right, so in a way, for the immediate topic of game physics, interactive physics, is we want to create a believable interactive world. In the setting, it's actually right, believable is crucial. We can simulate a lot, but if it blows up, if it goes wrong, that can really hurt. It can have the best graphics. If it does garbage, if the behavior doesn't match, that can hurt the reality. So it's important to really make it believable. And this is also then something that's really powerful to be explored by players. I have some examples later on. This can lead to or can provide a very nice basis for creating fun and nice gameplay. Or also it can actually reduce the amount of work to create a game. Again, later on I'll show some examples of games with physics, and in a way a physics simulator often can allow you to provide a large variety of behavior without actually having to manually create each of these different instances. Yeah, so we'll be following on numerical simulation algorithms, or actually one of the alternate ways of summarizing what this summarizing the goals of this lecture is like cool stuff you can do with numerical math. Hopefully you'll see quite a few examples over the course of the next semester. We'll deal with efficiency and stability. Also, it's traditionally a crucial topic within numerical simulations and one that we come back to a lot. And then also, being part of the bachelor track here in games engineering, we actually want to also incorporate a few very practical aspects, right? How do we get these things into working implementation? Yeah, those are the main goals of the course, and I want to give you a brief overview and outlook of the different topics we'll be dealing with, and that's kind of the summary here. Yeah, I don't need to read this, I'll just show you a few examples. So the starting point that we'll start with later today actually is starting with particles, right? That's in a way the simplest representation of a physical object in the computer. So we're just storing a position. So down there you can already see a small mock-up. We're basically assuming we have a infinitely small point that just, we know its location. Typically we also have a vector that specifies its velocity, for example. It might have a mass and some force acting on it. But these are typically very simple models. And in a way, what allows us to do very large particle systems is that typically they don't interact. So every particle is in a way alone. It has a few properties, but it just flies through space with some forces acting on it. It doesn't talk to its neighbors. And in that way, right, we can in parallel typically process very large numbers on the orders of many millions of particles. And here I have a nice small movie of some traditional particle systems from a particle system demo. Down there in the bottom you can see all kinds of stats of the current system, and I don't want to go into details what you're seeing here, but all of this is based on just on the order of a few hundred different points that act to relatively simple laws, some kind of driving force or some pre-specified motions. And then in this case it's actually neat because typically there's some kind of transparent billboard that's displayed for every particle, and that gives some surprisingly nice patterns. So here with these fire particles and a small animation, they change the color from yellow to gray, and that already gives a fair amount of complexity and interesting behavior. And in a way, key for making this interesting is there's a large number of them, quite a few. The next step towards getting more interesting, more complex behavior is to make the particles less alone. So next, what we'll also introduce in the lecture is to have a connection between selected particles. So springs. Here on the right you can see a small mass spring system with 4 particles and 3 springs connecting them. And from that suddenly now, instead of having isolated single particles, even if there are many, now we really have something to describe a volume and interactions in a volume. So typically not easy. There are all kinds of questions with respect to how to place, how to arrange them, how to keep these stable, but nonetheless there are really interesting effects that you can do here. And here's one nice example. Not a volume yet, but this is now a closed surface. This is a piece of cloth that collides with these spheres and falls over them and gives some pretty complicated behavior. As a kind of variant to model or for modeling 3D objects, we'll introduce rigid bodies. In a way, for rigid bodies, suddenly now we're taking things away. Now we don't have a lot of points that can move relative to each other, but for rigid bodies we assume it's fixed. We basically have something like a box or so that does not change, but just moves rigidly, hence the name. In a way, this is an interesting variant because if we do it right, if we change the physical model to incorporate this rigid motion, we can suddenly get very complicated behavior very efficiently. And this is what we'll be dealing with here. Again, there are some tricky questions like how to deal with collisions, collision responses, and stacks of objects, but nonetheless, this in a way is a good next step after the mass spring systems. And that is also a very traditional topic. I'm sure you've seen quite a few examples. This is a very old one by now. So this was possible roughly 15 years ago already. And despite being so old, the fun about such simulations is, as you can see here, we can run a lot of them and then have things like these crumbling towers of stacks of rigid bodies and get all kinds of complex behavior. So here, these are several hundreds of these boxes flying around. Slightly newer example, this is only 10 years old or so, from Bullet, one of the classic rigid body, real-time rigid body engines. So what's interesting here now is, compared to the previous one, now these demos actually couple rigid bodies with mass spring systems and or constraints, and suddenly you can actually get very complicated behavior, like this piece of rubber coupling the 2 rigid bodies, or you can imagine having kind of rubber ropes that constrain the motion of the bodies. And a few more examples will follow. In a way, this is another step of complexity that we will not fully deal with in this lecture, coupling different types of simulations. This is a bit what you can explore in the project towards the end of the semester we'll mostly be targeting the individual pieces for certain types of physics, like rigid bodies or mass spring systems. Okay, this example is not so exciting now, but there's more coming up. Right, this is just a non-extensible cloth. So this is the example I was looking for. Here we have now several rigid bodies with the strings and some deformable tori in the mix. So well, you can imagine if you go towards this direction, it can be quite complex in terms of behavior and also in terms of computations. Yeah, moving towards more and more complex physics, we'll also talk a little bit about fluids in this lecture, because this is actually a surprisingly tough topic, because in a way it's almost the opposite of a rigid body. For something like a glass of water or splashes or so, there's actually no clear shape at all. Water can deform in any way you let it, basically. Whereas a rigid body, it is fixed in its behavior and does not change at all, according to the model. And one classic example here is this one. This is a classic rigid body simulation, so one of the very first interactive ones. You can still see the individual particles that were used to simulate it. In a way, now we're back to particles, but here the main difference is that all of these particles, at least in neighborhoods, constantly need to talk to each other and evaluate pretty complex functions in neighborhoods of all the particles. So this little glass of water is actually, in a way, surprisingly complex to simulate. Play it again. So this is actually now already tricky to get fast in real time. But later on we'll be talking about as a kind of continuum model and perfectly plastic deformation. We'll also look at fluid simulations in this particle-based setting as an outlook. And right, this is actually, now it doesn't look so nice, but within these modern techniques you could make this look quite impressive. I also have a nice example later on. This is kind of historic simulation. Yeah, and with that I'm already at the end of the first part. Normally I'd like to take questions now regarding structure or content of the class. If you have some questions, please write them down for now, keep track of them, and join the Q&A session on Monday at 10, and then I'd be happy to answer these questions during the session. Or alternatively, also these Q&A sessions will be the main part where I'll be able to answer questions. If you have questions in between regarding the exercise structure or groups, then you is the right person to contact. You have the email address in the slides. Or later on, for specific questions regarding the individual assignments of the exercises, then please get in touch with the tutors. All right, but thanks so far.